So radian angles, arc length, which is just circumference. So here in my picture, my inner circle here is my unit circle, where I have radius 1. And then my next circle out here is not the unit circle, it has radius 2. And then I have another circle here with radius 3. So I just want to relate to the idea again of what is a radian angle and what is an arc length. So a couple things that you should store in memory is that if we have one revolution, that's 360 degrees, which is 2 pi radians. And again, reminder, what is a radian? A radian is a radius. So whatever circle you're on, if you take the length of that radius, 2 pi would be about what, 6.28. So that means 360 degrees is approximately 6.28 radians. And my claim was a radian literally means a radius of whatever circle you're on. So 1 radian is going to put us about here-ish. All right. There-ish. So that angle I'm drawing right here is 1 radian. And it is literally a radius on that particular circle. So then if I went around to 2 radians is, oops, let's get my pen out. 2 radians is going to be about here. 3 radians is going to be about there. 4 radians is going to be about here. 5 radians is going to be about here. And probably a little over more. And the 6th radian is going to be about over here. So, and then notice there's this little bit extra right there. So to get to this line right here, my claim is that is exactly, to the best of my artistic ability, 6 radians. Now, 6 radians is the measure from the positive x-axis going counterclockwise to there. This has a reference angle, and the reference angle is the measurement to the closest part of the x-axis right there. And that reference angle there, so that would be the reference angle, is going to be approximately what I need for a full rotation, and a full rotation is about 6.28. So that reference angle from 6 radians is going to be about 0.28 radians. What is it exactly? Well, all the way around is 2 pi. So whatever 2 pi minus the 6 that I took to get there is going to be the exact value of the reference angle. So the approximate value is way easier to do. If we want to double check that on a calculator, let's get a calculator out. So if we take 2 times pi minus 6, oops, not 8, minus 6, we get about 0.28 here. Remember, pi is about 3.14. If we double that, we get about 6.28. So it doesn't matter what circle we're on. Let's get back to the sketch there. Now, on the unit circle, 1 radian is exactly the same as 1 radius. So if I were walking on this circle and I covered a rotation of 1 radian, that means I've also gone 1 radius. So maybe the radius is in feet. I've just covered 1 foot there. If I were standing on the circle of radius 2 and I rotated around this central point 2 radians, I happen to cover 1 radius. How long is a radius? Well, in this case, a radius is 2, which would be 2 feet. And if I were on the circle of radius 3 and I covered 1 radian, that's the same as 1 radius on this circle, and the radius is worth 3 in that case. So relationship there between the arc length, the piece of the circumference that I covered, and the angle. The arc length here is just the fraction of the way around that I went. So you could think about it that way. So arc length is a fraction of the whole circumference. So if I'm on this circle of radius 3 out here, let's use that in blue. So if I have a circle and the radius is equal to 3, and I've covered an angle, usually we use the Greek letter theta to measure an angle, and I said, hey, my angle is exactly 1 radian. And I want to know what's the arc length I've covered there. Well, I know to go all the way around a circle of radius 3, that's the circumference. That would be 2 pi times 3. Now that's all the way around. Did I go all the way around? The answer is no. I didn't go all the way around. I only went 1 radian around, okay? So what fraction did I go around? Well, I went 1 out of the whole rotation. What's a whole rotation? 2 pi radians is the fraction that I covered there. So if I clean that up a little bit, what I get is the 2 pi's divide out, and I get an arc length of exactly 3 on a circle of radius 3 for 1 radian. So kind of just cleaning that up a little bit. What ended up being left here? Well, the 3 here, that was my radius, and the 1 there was the angle that I applied. So the relationship between arc length and the angle is with the radius. So in general, arc length is equal to the radius times whatever the angle is. Nice, simple relationship. Another way to think that is if we flip that around to think about another way another idea of what a radian means instead of being a literal radius, which it is a radian angle which I'm going to call theta for some generic angle. Could be this one, could be that one, could be something else. If I divide the r to the other side, it's always the arc length divided by the radius. If we're on the unit circle, the radius is 1. Dividing by 1 is pretty lame. Nothing happens, right? So the arc length is the radian angle. Otherwise, it's related to the radius. So this is a super important formula that will come up again and again. So radians and arc length relationship is very important. Other important thing is just getting used to radians, because we're going to be using radians more and more. Once in a while, I'll relate them to degrees just to help trigger some old memory of yours. Actually, I'm going to draw a picture of this. I think a picture is way better. So we're just going to focus on the first quadrant for a second. I'm going to draw my best circle here, or a quarter circle, which I'm way better at than drawing full circles. Not bad. And then some important angles here. So we know at the top here, this is an angle of 90 degrees, which is also pi over 2 radians. Down here, if we're at that point right there, we could call that 0 degrees, which is the same thing as 0 radians. Or we could call it, if we came all the way around to get there, full revolution, we could say it's 360 degrees at that point, which would be 2 pi radians. If I only went halfway through this arc right here, half of 90 would be 45 degrees. 45 degrees would be half of pi over 2, which would be pi over 4. Earlier, we did 1/3 of the way to 90, which is 30 degrees. And 1/3 of pi over 2 we found was pi over 6. If I go 30 and another 30, that puts me on the other side of 45 there. That would be 60 degrees, or 2 pi over 6s, which is pi over 3. And as we move through trigonometry, I'm going to keep referring back to this first quadrant of the unit circle and these reference angles of 0 degrees, pi over 6, pi over 4, pi over 3, and pi over 2. So I would recommend, like every night before you go to sleep, redraw this picture and put it under your pillow. Because I want you to think, you're used to thinking in degrees, we got to move on to thinking about radians. So when you hear 45 degrees, you think pi over 4 radians, or vice versa. If you see pi over 4, you should think 45 degrees, right? 1/8 of the way around a circle, half of a right angle. If you see pi over 6, I want you to think 30 degrees. If you see pi over 3, I want you to think 60 degrees. Pi over 2, right angle, 90 degrees. Super important you have these reference angles memorized and visualized. What do they look like? Okay, what do they look like if we draw a triangle with those angles in them, or if we draw a part of a circle, a sector of a circle with those in them there? All right, next.